Okay, hi, I'm Kate Kraft. I'm just kind of coming in to doing a little bit of work thinking about Ceres. I've done a lot of my modeling and things before with Europa and Mars as well, sort of earlier on. I just thought I'd give a little background, although by this point we've heard a lot of background, so let's just go through it really quickly. We see a lot of volcanism in our solar system. There's evidence of molten rock variety observed on many rocky bodies, but we have a lot of questions about how cryovolcanism may be occurring. Like we see obvious cryovolcanism with Enceladus and its plumes, but where have we seen evidence, or is it really evidence that this like liquid, salty, molten-ish, icy water has come to the surface and flowed on the surface of some of these icy bodies? We see features that indicate this. We see raised morphologies, fractures and fracture systems, morphology that overlays older terrain, salt deposits. We see active plumes and plume deposits. And then the Dawn spacecraft has imaged several of these on Ceres. And so I'm interested in modeling what we think might be a magma chamber below the surface at the Akator crater, where they see a gravity anomaly, and then think that possibly there is this cryomagma chamber at depth. And we also see evidence in this crater of salts at the surface that could indicate cryovolcanic activity at the surface. But then when we want to think about how this activity is happening, so terrestrially, one of the ways that you can get volcanism is that it can occur due to density contrast and overpressurization. Potentially, cryovolcanism also occurs this way. Overpressurization during freezing in the subsurface chamber could drive fluids towards the surface. And then, as was mentioned just recently, you could have a tidal pumping type of mechanism occurring at some of the icy moons, where the fracture is opening and closing and pumping the fluid towards the surface, and maybe also potentially releasing volatiles. One place we see this evidence of a overpressurization on Earth driving magma towards the surface is at the seafloor, and some of the axial systems where we see off-ridge, we'll see the black smokers and the white smokers. And they've done studies where they've been able to model where the magma chamber occurs. So the magma chamber here, and they've modeled the diking process towards the surface to where they can get it to line up where they see the actual surface expression of the dike at the seafloor, as well as the seismic activity that aligns then with that dike process. And so then if we wanted to think about that happening on an icy moon, we can consider that you might also have a chamber at depth that could overpressurize and then cool, and so that cooling is what's overpressurizing the chamber at depth. And we can model this then with the finite element codes. And I'd just like to kind of go back a little bit with our discussion today. Is like I've done some modeling where I'm a sort of a fan, or I think it's plausible that you could have fracture initiate within an ice shell, a cooling and thickening ice shell that could initiate a fracture within the ice shell and then open downwards towards the ocean and allow water to flow up in. But I am kind of a skeptical, or I haven't seen proof enough of how you could actually get that fracture to turn and make a sill in the horizontal fashion, because really the stress field for a homogeneous ice shell is such that it wants to drive any fractures vertically as opposed to turning and making a sill. But that being said, we see evidence at the surface, including gravity anomalies, that indicate that we might have these subsurface water pockets, and so maybe they exist somehow. So I'm going to start from that point, where we have this subsurface cryovolcanic chamber that's overpressurizing. This is my model setup. So I'm modeling this in 2D, where we look at this magma chamber or cryovolcanic chamber here that's filled with cryo fluid and is then cooling and overpressurizing. And so the pressure that's induced within the cryo chamber is 1 plus whatever % of overpressurization you want to add, and then you have the overlying lithostatic load. And so you consider then your material parameters, and you have gravity acting on the system. So this figure just shows the overpressurization here that's acting outwards on the chamber. And then using this model, I can calculate all the stresses that are occurring around the magmatic body, and it will indicate for me where the highest tensile stresses are occurring through at that magmatic body. So this is a model I had done previously for Mars, where I actually looked at a diking process, but then thought about how that would induce through thermal, the thermal gradient that was induced by the dike and the heat from the dike would induce groundwater circulation and might be able to bring water to the surface on Mars. But the same process could be happening, and then this model can be used to calculate where you get the highest tensile stresses, and that would be where you might think a fracture would initiate and then drive upwards from the magmatic body. And so this is the model then that I've done for Ceres so far. And so we started with just material parameters, and I started out with the more like the carbonate parameters that I pulled from a paper, and that's in press, Deborah's paper that's in press. And she did a nice job. She showed her table yesterday. So I pulled those parameters out and just employed those to get more accurate material parameters for Ceres, at least what we think is there at Akator crater. And so using those parameters and the gravity of Ceres, I can employ that, and then it will tell me what the stress field is, assuming those parameters. And so using that, I can then pressurize this internal magmatic chamber, and I can see where the highest tensile stresses are acting. So typically, and it's the same as what we see with terrestrial and Mars models, the physics acts the same. We just get different values as your outputs. And so we are getting these highest tensile stresses sort of at the edges of the magmatic body. And so you can use the model to actually find kind of exactly where it's happening. You can see the highest stresses there. And Laura did an excellent job, and previous speakers have done an excellent job of sort of explaining to you how fracture mechanics works, and so what you're acting against the lithostatic load, as well as the tensile strength of the crust. So you have to overcome those to initiate fractures. So you just have to make sure that these values are high enough to overcome that. So when that all works out and you can initiate a fracture, you can then use the program to for each propagation step, it recalculates the stress field, it recalculates the stress at the fracture tip, and you can allow the fracture to propagate where it wants to. It's going to want to propagate either perpendicular to the maximum compressive stress or in the direction. So it's perpendicular to the maximum tensile stress or the maximum compressive stress. And so it propagates upwards, and it can reach the surface. So remember, again, this driving pressure is from that cooling and thickening in here inside this internal chamber, and it drives the fluid up through the dike towards the surface. And so we were able to calculate that, find out where it ends up there near the surface, and it's able to reach the surface and potentially provide fluid to the surface there. And so I guess basically just in summary, these models I think are pretty powerful. They allow you to explore a lot of different parameters. So we can use them to think about where, if we see a surface expression of a dike at the surface and we think there's a magmatic body in the subsurface, we can use it to figure out where that magmatic body lies beneath the surface expression of the dike. We can consider different material parameters for different bodies, different gravities. We can change that hydrostatic pressure. We can have it decrease as you allow the fluid to move out of the chamber. In reality, that driving pressure is going to be decreasing with the loss of fluid unless you have replenishment that's acting. And then other things that we can consider, which is something I've done a little bit of with Europa, is thinking about fracture interactions. So a lot of our models, we only think about one fracture. And so in reality, fractures will interact with one another as long as they're in close enough proximity with one another. And so we could think about with Akator crater, especially like for a place that's had an impact, maybe there were, was a set of fractures and a fracturing system that was induced by the impact. So anything that had been coming close enough to the surface could potentially then join together and make a pathway to the surface. And then we can consider material layering. And then also you can actually induce a deformation to the system, and it will calculate the stresses, and you can see what effects, say, for tidal bulging, for example, might have on your propagation of your fracture. It can change the direction of the fracture somewhat. And then thermal stresses as well. So if we have a fluid intrusion, it's going to cause thermal stresses to be occurring around that dike intrusion. I have not incorporated that yet. One thing that we're just starting to think about as well is just some calculations that my co-author, Catherine Walker, has done, is that if you have an intrusion beneath the surface and it's cooling and thickening, the volume change is going to cause some uplift at the surface. So if we assumed she looked at various different overpressurizations and got a range of, oops, sorry, wrong button, a range of uplift over that sill where we had assumed that sort of 10-kilometer thick and 100-kilometer wide sill beneath Octur. Okay, and so in summary, this finite element modeling shows that this carbonate type of magma with 1% overpressurization can reach to the surface or the near surface at Octur. And the dike tip would be towards the end, one end or the other, because they were both, there were high tensile stresses at both sides. And so that could indicate for you, if you see surface expression, where that magma chamber could be lying underneath. And then Catherine's calculation showed that for 1 to 2 megapascals of overpressure, you get about 100 to 200 meters of uplift. And future work, we're interested to investigate more of the interactions with surface fractures or near surface fractures that might be coming from the surface, those interactions. Think about the effects and do some calculations using the models to consider thermal stresses. We reduce the pressure as the magma leaves the chamber if we want to think that no replenishment is actively happening. And then continue to apply these thoughts to other bodies. And with that, thanks.
It's more of an encouragement on your next round of models. I've done a lot of work in the Basin and Range, western U.S., and there's a lot of intrusive basalts throughout different rock types.
Yeah.
But what we see time and time again is that it will start as a dike, move to a sill, become a dike again, and then a sill. And where it becomes a sill is almost always in a mechanically weak layer. And so I'd be really interested, you had in there putting in that layering.
Yeah.
And I'd be interested to see how that might impact things if you have a couple of just mechanically contrasting layers.
Yeah, and I did that for Europa, actually. I tried to consider that because I know in the terrestrial realm. And my model, from the model, this program, it just bypassed that layer with a very slight turn. But I don't think that the model, this program at least, can actually consider sort of like that unzipping, that delaminating kind of process. And so I am really interested to try to figure out how to incorporate that possibility. Although,
how are you incorporating the faults? Can you do that as beds?
Oh, yeah, possibly. Although I don't. So when I incorporate a fracture in this, it's just like an open space, and so I don't think then I'd have to model it as maybe a different material, but maybe I could model it as a different material so the program, it doesn't run into this open space. But I wonder for icy bodies, and maybe it's different for Ceres, but we tend to think about them being fairly homogeneous unless maybe there's a brine layer there or a drastic change in porosity, say, or something that maybe could make a kind of layering. But otherwise, for icy bodies, it's maybe not so layered.
Well, I think I was specifically thinking somebody earlier had been talking about fern and the differences so on these
porosity.
icy moons we might have those
Maybe,
contrasts.
yeah.
I don't know how big it would be though.
Yeah, very nice talk. Yeah, so on Ceres we have evidence looking at the polygonal craters that there are a lot of faults. It's like, I don't know the depth of the faults, but it's fractured all over the surface.
Okay.
It's really, and I don't think we have really, on the Don team, we have really started thinking about the implications of this on the motion of material to the surface.
Okay, thanks.
More questions for Kate?
I might have missed it, but in your
In your calculation of the uplift, or Catherine's calculation of uplift, how far below the surface was it presumed that
she assumed the same parameters that I did for the chamber.
Okay.
So it should have been 40 kilometers below the surface, because that's, I think,
seems like a lot of uplift
yeah.
for something that deep.